record. So last time we talked a little bit about pointers and memory allocation, and I just wanted to do a practical example today of that that you guys should all pretty much be familiar with. And then I'll probably talk about assignment 4 on Monday, but I'll put it up either later today or sometime tomorrow. And I believe that one has to do with pointers. I haven't looked over it in full yet, so that's why I wasn't going to go over it today, but I am going to put it up if you want to look at it. Yeah, because I just got it recently, so I didn't take a super long look at it. But anyways, let's program something, but let's think it out first. So we started to do this example at the end of class last time, and I just kind of wanted to do it as a practical example because I think it's a good example of how we can use dynamic memory allocation to do things nicely. So we've been using vectors this whole time, so let's try ourselves to make a vector, and we started to talk a little bit about how exactly a vector would work. So as per usual, we have some sort of memory space where we have these blocks of data that could be any number of bytes depending on what it is we're actually dealing with. Okay, and so if I wanted to make a vector, we've been accessing it like an array, and it really is just like an array. Except the main thing about a vector is that every time we push something, it gets a little bit longer. So if I was to do an example here, I might have a vector of, let's just say, integers. So we'll do integers today, and then probably another example as well. A vector of integers, and let's just call it list. So what that does is it goes into memory, and there's basically a pointer at least to where this is, but it doesn't actually allocate any space because it's an empty list to start with. So what will happen is it will start to actually allocate the memory as we append things in. So I could do something like list dot pushback number 4. And that would go into memory here, and it would create a cell, and it would put 4 into it, right? Maybe it's better if I do this horizontally. So that would go over here, and it would make 4, right? And that's all that would be. So the size of this one is now 1. And then if I was to do something like list.pushback, 7, then it would go into memory, and it would now say, oh, I need to add a second one, so let's add a second block of memory, and it would put it there, and then the size would become 2. And so the same thing would keep happening the more and more we push onto it. It's just going to keep making space for the next element, and then actually putting it in there. And it might be doing it a little bit differently than the way I think we're going to try to do it today, because I think we're going to try to do it a common sense way. But yeah, it doesn't allocate memory until it actually needs it, right? So unlike an array where I would say something like R4, or int R4, something like that, and then that just makes 4 blocks of spaces that we can put things into, and that's all that it can do. And if I wanted to put 5, I have to make a new array, or reconsider what I'm doing. Or maybe I only need 2 things, and then I fill this space and that space, and then these are empty, which means I'm wasting some space. As opposed to that, where I'm stuck with a fixed amount of space, I can resize it. So what we want to do is essentially allocate some space whenever we get that pushback, So again, if I was to say list, I'm going to say add for this one. We're going to use some different names here, but they really do the same thing. So if I was to add something like 4, what I will want to do is I'm going to need to have a pointer, have it point to that area, and then put the 4 into it. And then as I add more things onto this, we could certainly make it take more contiguous space here, but that might be a little bit more difficult. We're going to want to determine when are we out of space. If we are out of space, let's allocate some new area. So if I, for instance, add 5 here, I only allocated this one block, so I might copy them over to a new location and then get rid of the old one. So we started that a little bit last time. Right, so I might have a pointer there. Right, and then we'll basically keep track of how big this is as well. So we'll keep track of something like size, like they do with a vector. And so this one, right, went from 1 to 2. So we'll do something like that, which we kind of started on last time. So that's why I'm just briefly doing it, not going into a whole lot of detail. But if you have questions on it, totally stop me, because this is just the general idea of what we're going to do. And then we'll talk about ways we can optimize this a little bit, and then maybe implement one of the ways to optimize it, but probably not the efficient way, which is what I imagine the actual vector does. Okay. So let's just quickly go over here. So let's just make a class. Actually, let's make a header file for the class. Move that down a little bit. So yeah, let's go here and let's make a header file where we'll put this list class that we're going to make. So we'll make a new item, make a header file, and we'll just call it list.h. And then we'll not use a namespace. I think it's fine. So class, we'll call this one int list, and we'll go over at some point how you would be able to do it for any data type without having to rewrite it every single time. So you'll notice vector, right, has those angle brackets, and then it lets you put a type in it, and then it will store anything. There's a way to do that, but we'll talk about it at some point, about templates, that is. Okay, so what I'm going to need for this integer list is, and we'll comment really quick here. Let me zoom in a little bit. I've noticed it's been kind of far out for the past few classes. This is a vector-like class that dynamically allocates memory as it needs it to store things. Right. So what we'll do is we will keep track of an integer pointer, which is going to point to the data that we actually need. So we'll call that maybe data here. Oops. Just data. And we will use that to hold that array, and then basically allocate the array to be the size that we need it to be whenever we need it. And we'll be able to do that with a pointer. Whereas if we had a normal array, we could only allocate the space once, right? We just give it a number, and you know, that's it. So really, we just need that and the size, and we should be fine. And we want both of these to be private because, oops, the person using it doesn't need to know where our pointer is, and they probably do need to know the size, but we don't want them to modify it or change it, right? So we'll just make a getter for that one. Actually, we'll need to make a getter for both of them because obviously they need to be able to access the data. With a vector, they do that with the index thing like this, right? With the left square bracket, right square bracket. And again, there's ways we can do that with operator overloading, but that's something we'll talk about later. For the time being, let's just make a function. I don't think it'll be too hard to read. So let's make a function first off that returns integer get at. Maybe just at. So this will return the data that's at that index. So we'll say int index, and then we'll return that in a moment. Actually, let's do it right now. So again, consider data is going to be basically an array, and if you remember from last time with the way pointers worked, is if we allocate space to be an array, we can access it just like an array. So what I can do is I can say return data. Sub index, and that will get the data at that index, basically treating it like it's an array. Well, because it is. The pointer is pointing to an array. And we could do some more error checking here, make sure that the index is actually in bounds and not negative and all that stuff. Or we could let the compiler, or not the compiler, but we can let the system just crash at runtime too, I suppose. So maybe we'll just throw in a check here. So if index is greater than 0, actually greater than or equal to 0, and index is strictly less than size, then we'll return that. Otherwise, maybe we'll just return 0 as a safe thing. Okay, so basically we just say if the number is at least 0, which is the first number we start counting at for an index, and it's also less than the size, which would imply that it's size minus 1 or smaller, then it's fine for us to get the data because it should be there, assuming we've done everything right, and then we'll just return 0 if there is no data for us to access because the user is going out of bounds. Alternatively, we could just not write that and then let it crash because the user is going out of bounds and they should know it. Okay, so that's first part, and then getting size, that one should be pretty straightforward. So that's just a normal getter. We'll just put something here to let the user get the size, and that will just return the size. All right. Now comes the part with the dynamic allocation. So when you consider what a vector does, you have the ability to add to it, and you have the ability to get to it. So push back and get. And then you can also pop back, but we won't do that for now. We'll just stick with the pushback. And the way you would do pop back, I guess, to mention, is it would involve keeping some more pointers. I'll talk about that at the very end, I suppose. There's a better way to do this that will be more efficient. And we'll talk about two ways to do that. One, the way that the vectors do it, and then one, another way to just not allocate as often. But we've already got the getting part, I suppose. This is like the indexer, and then we need the adding to the end part. So let's do a function that does that really quick. We'll just do one called void add. And all this will do is it will add to the end of list. To the end of the list. Okay, so the way we currently have it set up, we have to allocate space every time they add something, right? So if I had this original example, when it was 0, I had nothing, and then I added the number 4, and then I had to allocate one block to put that 4 into, and then I put it in there. And then when I had the 5 added, I had to allocate 2 blocks now, and then add the 5 in there, copy the 4 over, right? Because we couldn't put the 5 here because we only had one space allocated, so it was all we were allowed to use, and then move it somewhere else, and then basically free up the space. So every time we get something, we're going to want to allocate space. So here we will say, again, like last time, we did a little bit of this example. If I was to, okay, let's outline this a little bit more in detail. let's go back to let's just clear this all out. We'll do it a little bit better here. So when I initialize it, I'm going to have size equal to 0. I have some memory space, and I'm going to have nothing allocated. So we have a pointer called data, and we'll get to it in a second in the constructor, but we'll just make it null. And so what we want to do when we add 4 here is if it's null, it's okay to make it just point there, right? We'll say the data pointer, that's a star, I guess, but that's okay. The data pointer is pointing to somewhere, and then we throw in the data. And we know we would allocate the size that we need, which will always be 1 higher than that one. Right, so if I was to go to this line now, to add 5, the idea here is that this blue part is what I've allocated. It's what I'm allowed to use. So I don't have space to put the 5 in. There's obviously memory there, but I'm not guaranteed that in a real system because maybe this is at the border of where another program is using memory, or it's just somehow coincidentally at the very, very end of RAM, and so I don't have space after that. So I might need to reallocate some space and then move this over. So consider if I was to just allocate new space for data immediately and say I wanted to allocate 2 for it and then copy over the 4 and then add the 5. I can't have this data pointing to 2 things at once, right? So by making a new array there, I'm going to lose that pointer, which means that I wouldn't have been able to copy this 4 over because I would have had no way to look at it. And on top of that, even if I did have a way to look at it and copied it over, then there's a bit of an issue because even if I just copy this over, again, we talked about this a little bit last time, this 4 is just there. It's still allocated, this blue part, and the system can't use it because it thinks we're still using it, but we have no pointer to it, so we have no way to get back to it, which is, again, called a memory leak. And we want to avoid that as much as possible because if you allow too many memory leaks, then you're going to run out of memory, and then your program is probably going to be kicked out by the operating system. It's going to crash, or at least terminate. The OS will stop it. So what we're going to have to do is make a temporary pointer, have that point to there, keep the data pointer that we were using before, have that keep pointing to the place that it was while we copy things over. So now I have a way to access this 4, right? I can copy it over. And then once we're done, we will deallocate all of this space that the data is using and then make the data point to where temp is by copying it over, break that link, and then temp will basically delete itself because it's going to be a local variable in our function, and we don't really need it anymore because we don't need 2 pointers to the same thing. Does that all make sense, like the general outline of how we're going to do this, or does anybody have any questions on that? I don't see any questions, but I'll keep going. So let's try to do that here in our code, and obviously to our integer list we want to be adding integers. So we'll say int new int. Alright. So again, to run through what we were going to do is we are going to allocate some new space with a new pointer, copy things over, and then basically deallocate the old space. So first thing we'll have to do then is allocate the new space. So I'm going to create an integer pointer called temp, like we just had, and I'm going to allocate some memory. So 2 things about that. Does anybody remember how we allocate memory, what keyword we use, and then also what's the amount of size that I need for this? How can I figure that out? So first things first, does anybody remember the keyword? New? Yeah, you guys got it. So new, that allocates some new space. And then, does anybody know what or how I'm going to figure out what the size is? And actually, I should probably make a constructor first here. So let's make a constructor really quick for this, just called list. That takes nothing. And that should initialize it. So I should have done this first, otherwise this probably doesn't make a whole lot of sense. Let's make the size 0 by default, because when we create a new one, there's nothing in it, and then we'll just make the data point to null. Null is undefined. Is that in namespace standard? Maybe it is just a constant. No? Is that actually in a library? Usually that's a keyword in most languages. I didn't even know it's all caps. I guess that's an IO stream. That's really strange to me. Define null. 0. Okay. Or it's called null pointer as well. Is that a constant they have? Null pointer? Oh, that's interesting. Huh. I didn't know that. It's usually just like null. I mean, every language has a different name for it, I guess. But okay. Well, I guess that's nice to know. It's an IO stream. But I guess regardless, let's just initialize it to null. I guess you can use null pointer as well. And that probably doesn't require this deal. But anyways, yeah, what we were saying. So let's initialize the size to 0 and the data to point to null, and then we'll just update it as we need it. So we're going to allocate some new space for the array, and what's going to be the size of the new array we make if we originally had size amount of data. So let's just say size was 1, and I'm going to make an array of 2. How do I figure that out based off the size? So in that case, it would have to be the size of the last one, and then we're adding 1 to the new one, right? So one way we can do this is we can just say it's size plus 1. And this will work even when it's 0, if you notice, because if the size is 0, this will allocate 0 plus 1 space to put the new thing into. And then we'll expand upon this in a second. So we created the new space. We want to copy everything from the old array over, and then keep going. So let's really quick copy that over. So int I equals 0. We can then go from I less than size and I plus plus, and then copy over to the new temporary array the old stuff data. So I. So consider that the data array is still a size because I haven't changed the size variable at all. So this is just going to copy over from I equals 0 to size into the original, and then any space that's after that, in this case just the 1 space at the end, is not going to get set in temp yet because of the fact that, well, it's not going to get captured by this for loop. So this will copy the data over. Space. Okay. And then after that, so we've copied over all the data. We want to make the old pointer point to this new one. And we also want to deallocate it. So what order should I go in? Should I deallocate it first and then copy it over, or copy it over and then deallocate it? Copy then deallocate. Copy then deallocate. I'm seeing 3 copy and then deallocate. So consider if I did that. Really quick. Let's just erase this. So the point that we're at right now is something like this. Oops. Where data is still pointing to the old one, right? So this 4 is still there right now. So let's say we had an original array that was 4, and we've now allocated temp to be 4 and 5. If we copy data to be temp and then deallocate, we now no longer know where that space is. So if we copy first and then deallocate, we're actually going to deallocate the memory that we just created, and the old memory is going to be still there, but we don't have a way to get to it, which is going to create a memory leak. So we're going to do it the other way around. We're going to first deallocate this space. So while data is still pointing to it, we'll deallocate it. We won't have the ability to access it anymore while we're still pointing to it, but that's okay because we're not going to access it. And then we'll copy the pointer over to there. Like that. Okay. So hopefully that's clear. It might be a little counterintuitive, but we want to, make sure that we're still pointing to the data that we've gotten rid of for just a moment and then copy it back over. Otherwise, we're going to lose the ability to access it. And then we'll overwrite the stuff we want, and we'll get probably some read errors if we end up doing that. So yeah, we said we want to deallocate it first. If you remember, that's with the delete keyword. And then I put brackets to specify that I'm deleting an array versus just deleting a normal value. Okay, so I want to delete the array, and I'm going to delete, I call it data. So I'm going to delete the old data. Which again, just remember, it doesn't actually mean it's going to like physically delete it, wipe it, and make it 0 or anything. It just means that it's going to allow the system to use that memory again, and then it could do whatever it wants with it. And then now we'll copy the pointer over. So temp equals, or data equals temp. Allocation. And then, yeah, that takes care of at least allocating the new space and copying everything over. But with the current way I have it, I still haven't actually added the new integer in yet. So let's do that really quick. Which we could have done here a little moment ago, but I'm moving it to the end just for the sake of moving it to the end because I'm going to change the code. So now let's add that to the very end, and that will be at, actually first things first, before we do that, normally I'd write plus plus, but let's put size plus equals 1. So the size got 1 bigger now because I allocated 1 up here, and now I'm actually done using the size for the old data, so I can update it to reflect it. Okay, so let's update the size to be correct now, and then the last thing we need to do is actually put it into the array. So we can just say data sub size -1 equals new integer. Okay, so that should take care of that. We have this here. So let's just make sure this works really quick, and let's see what it does. So we'll make an integer list. It would help if I actually included the header. Include list.h. Let's make an integer list called list. And then let's list.add 2, list.add 5, list.add 9, list.add 12. Okay, that all seems to be fine, and then we will go through and make sure the at function actually works as well. So for int I equals 0, I less than list.get size, assuming that size is getting updated correctly, then I plus plus. and then we'll see out list dot at I. Okay, so this should now go through and add 2, 5, 9, 12, and then print all the stuff that I added. So let's make sure it works first, and then we'll take a step-by-step through look at it just to make sure that it's okay. Okay, and you can see, yep, that seems to be the case. Let's zoom in a little bit. So it prints 2, 5, 9, 12, so it seems to be working. But we can always actually make sure that that's the case. So let's take a quick step through what it's actually doing. So if I run it, we'll put this off to the side. So we're on the first line here. If I step into the next line of code, you should see that it did the constructor pretty fast. You can see here in the data section, I don't think I can zoom in on that. We have data pointing to 0, 0, 0, 0, 0, which is null, and it has a size of 0. And so as we go to add, it will create the new pointer. So this is a reference to this. Yeah, so this will keep track of the data and the size. Temp is now pointing to a new location. Yeah, sorry, it doesn't get set until the end of the line. So now it's pointing to a new location. And you'll see that it has one element below it because now the size is 1 that the temp is allocating. It will copy nothing over because size was currently 0. So 0 is not less than 0, so the for loop gets skipped altogether. We go to delete data, which I should check actually if it's null. I'm surprised that didn't crash. But it seemed to be okay with the fact that I was deallocating null. We set data to point at new stuff. We increment the size. We add the new integer. And so by the end of this, you'll see that if I look at the data pointer, it is some address. It's the address that temp was pointing to, which is where we allocated the new array. And it has one element, which was the 2 that we added. Again, sorry if this is a little hard to see. I don't think there's a way to zoom in this part of Visual Studio. You're just going to have to trust that it's all correct, I suppose. But let's just make sure it does the same thing for 5. So you'll see here, allocates a temp pointer, or makes a temp pointer, has it point to some random memory. Oh. That's strange. That appears to be pointing to nothing. I0, temp equals 2. Makes the size go up by 1. Well, I mean, it was clearly working earlier. Why is it not showing that? I wonder. Maybe it only shows the initial thing in the C++ debugger. Well, that's unfortunate. I guess it doesn't really show much, but we can see that it is updating it, and it seems to be allocating the space and whatnot. So the rest of them are going to proceed similarly. It's going to allocate one block of space, and then add it to it, and then do all the stuff we described. And then, obviously, it prints it. This is a little unfortunate that the pointer doesn't show all the array contents. Maybe it's just because it knows it's an integer pointer and it only points to the integer that it's actually pointing to. Is there a way to check for a memory leak? Unfortunately, no. At least not like programmatically, if that's what you mean. So there's no function or anything that's like, is memory leak. But that's a good question. So C++ does not do any sort of checking. It leaves it all up to you in hopes that you are a good programmer and that you aren't doing any memory leaks. Other languages that use garbage collection specifically, which C# does, I think Java does. Python might do a combination of both. I think it might let you do garbage collection and managing the pointers yourself. But those languages don't actually let you like directly interface with pointers, and so if there is a memory leak, it takes care of it itself. And what it will do is essentially, we won't go into a whole lot of detail, but what systems like those will do is they will pour through, look if there's any pointers pointing to data that you haven't used or that's not going to be used in the rest of your code. Actually, I guess on that note, Python shouldn't do it. That's probably why it has a delete keyword as well. I don't think it would be capable of doing that with an interpreter. But I digress. It will pour through. It'll look for any pointers that aren't pointing to anything anymore, or data that's not being pointed to, and it will deallocate it for you. And it will periodically do that on a fixed amount of time every once in a while. And that's called garbage collection, which a lot of languages do, at least modern languages. C++ does not. They expect you to actually deallocate all the memory yourself. So if there's any memory leaks, it's your fault, and C++ is not going to fix it for you. And that's both a good thing and a bad thing. It's a good thing because it means if you do remember to actually fix your memory leaks, then it's going to be really efficient. You take care of it immediately, and you don't have to waste any time actually looking for all of those memory leaks, all those dangling pointers. But it's bad because if you don't actually address the memory leak, then you have memory leaks. So it's it has a pro and a con. The pro being that it's faster if you know exactly what you're doing with the pointers, and it's bad if you don't, because then now it's going to be pointed to nothing if you make a mistake. And even if you're an experienced programmer, sometimes maybe you'll accidentally do that, which is why a lot of languages are now opting for garbage collection. But yeah, good question. That is something that most languages address. C++ doesn't, unfortunately, for efficiency's sake. Maybe there's a library that does garbage collection, but I'm not too sure. So maybe there is a way, but as far as I know, it doesn't. Anyways, any other questions regarding this stuff at all? Why we did each individual step, I guess, in this part, and exactly what a pointer does. Okay, so let's try to optimize this at least a little bit. So one problem with the current setup that we have is that every time we do an addition to the list, I have to allocate memory. So when I did this one and I added the 5 to it, I had to allocate memory, and if I had to add a 7 to the end of it, I would have to allocate memory and copy things over, and then if I went again, I'd have to allocate, copy things over, and that takes a bit of time. So this is not very time efficient because of the fact that I'm going to have to copy things over every single time in order to make that new allocation. And, that's not great because repeated allocations, especially the ones that are getting bigger and bigger, that are going to take more and more time to copy things over, that's going to make us wait a long time. So can anybody think of a way that we can maybe make this faster? So there's two ways that we're going to discuss. There's one that's maybe a little more common sense, and then the way that the vector probably actually does it, which is better. So is there a way that we can improve on the fact that we're allocating every single time? Is there a way we can do it less frequently? So consider, what if when I went to go add 5 here, instead of allocating just what I need, so I needed 2 in order to do that, what if I allocated like 4? And then I keep track of what the actual size is still. So this would still be 2 actually for this one. And then I make sure that I have extra data here, and I can keep track of that with something like count. So if I did something like that, then the next two additions I do, I already have space allocated that I can throw it into. And you might be questioning me a little bit because I was talking about earlier how the advantage of this is the fact that we don't have any extra wasted space, and this does it, and that's fair. That is a problem with this this line of approach, but the idea here is that if we keep the number small enough, we won't really waste that much space, and we get at least a little bit more efficiency out of it. Yeah. So if I had an array of 100 things, and this count at most is going to waste, if I add, in this case, 2 more extra slots than I need, it's going to waste at most 2 extra slots, and that's not a whole ridiculous amount of data. If I have like 100 or 1,000 things in my list, 2 extra, integers, just 8 bytes of data, that's not a ridiculous waste. And it kind of makes up for it in the fact that we're going to allocate, maybe half or a third of the amount of time, and we don't have to copy over as often. So really quick, let's try to implement that, and then we'll just briefly talk about how the vector likely actually does it. I don't know of the full implementation, but it would make a lot of sense, at least the way I'm thinking of doing it. Yeah, so now let's create 2 things. Let's create an integer called count. And so this one will keep track of, how many things are in the list. This one will say how much space is allocated. And then we will create a constant integer called, I don't know, expansion size, something like that. We'll make it 4. And this will be how much extra space we allocate every single time. Okay, so now let's try to change this a little bit. So this is the whole allocation. This was the addition part. So add the new int to the end of the list. So the addition is going to be pretty much the same, and we want to do some stuff here. So I'm going to make this still size ++. I can actually be fine with that because I'm going to use count. So this stuff here, this is the actual allocation of new space. So I only need to do that now if there's space that I'm not currently using. So we can check that by comparing the size. So the size being the actual amount of things in our array. So if size is currently equal to the count, then we know we need to do an allocation. Because if count is how much space we've allocated and size is the amount of things in our array, then we know if the amount of things has taken up all of space, in other words, if they're equal, then we should do an allocation. Okay, so hopefully that makes sense. And then really quick, let's just go down here and we'll make sure we allocate, or sorry, not allocate, we initialize count to 0 as well. So we have no space initialized to begin with and nothing in our array. And I guess the nice thing about count is that it can be an example here of a private variable that we're not even going to put a getter or a setter for, because the user doesn't need to know anything about count. They don't need to know anything about expansion size. We can keep those secret and they can just pretend our thing actually works, which hopefully it does. But anyways, so now we know we will only allocate when that's the case, and rather than allocate one space, and I'm going to allocate based off the count rather than the size, we will allocate for the count plus the amount of space that we're going to do every time, which I called expansion size. So now, for instance, if I was to need to allocate, which is what that says, then I'm going to allocate a space that is the current size, and then it's bigger by the amount that we want to expand it by every single time. So in this case, it will expand it by 4 longer than the old one was. And then this will continue to do the same thing. It will copy everything over. There's nothing we need to change about that. This will deallocate it, and this will copy it over. There's only one extra thing we need to do now, which actually we can do it a little bit more efficient, but this is okay. I'm just going to throw this down here for the sake of readability. So we will update it to reflect how much space we've actually allocated. So update count to new allocated space size. All right, and then the rest of this should work, right? There's nothing different that needs to be done. It will copy over everything. The stuff that's to the right of size, which is the new allocated count, the new allocated space that we have from the count, that's not going to get copied over. It's just going to be random garbage, but that's okay because we're not using it. And then we'll delete the old data and copy the pointer over, and there's nothing extra about that. And then this stuff here will work every single time. So consider that this will always add to the next position in the array as far as the size is concerned. And I'll probably draw a diagram out in a second here for this, and then add it to that position. So this should work fine, I think. I don't think I made any mistakes, but we'll find out when we run it. So let's make sure that works really quick, and then maybe I'll actually draw it. So let's go to this first one. Oh no. Let's go to that first one. Where'd the window go? There it is. And we'll throw this off to the side. We'll see here it adds 2. If we look at the variables, nothing is set currently. Just because it doesn't really know, I guess, when it starts a function call. And it says the count is 0, the size is 0, and so they'll be equal to each other. It will allocate new space. So temp will now point to some space. Again, it will only really show me the head, which is not particularly useful, but that's okay. And it will make the count go up by how much space we allocated, which was 4 in this case. So we always wanted to allocate 4 spaces. And then it will copy over all the data, which is none currently because we started with 0. It will delete the old data, which is a null pointer and does nothing. And then it will copy it to point to the new one. So this points to where temp was just pointing to. And temp now gets deleted because it was a local. So we don't actually see that it matched, but if you, I guess we're paying attention earlier, which I wasn't, but it should have been the same pointer, this same address here. And then it will make the size go bigger and add it in. So the size now becomes 1, and this will add to position 0. Right, and then you'll notice for 5, we'll just check that one really quick. The size is 1 because we have one thing in the array, but we allocated 4 blocks of memory. So it won't need to reallocate any memory. It will just add 5 to the end. And if I continue and let it just execute normally, you should see that it still does the same thing. It still adds all of them and prints all of them out correctly. But it doesn't allocate as often. It only allocates every 4 elements that I add. And also the first time I add something, I suppose. So that's good. That's a little bit more efficient because it doesn't have to copy over every single time. But maybe it's still not the best that we can do. So really quick, let's just get a visual representation of what exactly we just did. So consider that we had something called data. So let's do a more interesting example than the empty one. Let's say I have a array that is 4 allocated spaces. So count equals 4, and we'll say size equals 3. Say this is 2, 5, 9, and this is just garbage. This random garbage. Okay, so consider if I had 2 lines of code now. So let's say I went to my list and I added 1, and then after that I went and I added 8. So what's going to happen when I do this first add is it's going to go here and it's going to check, are the size and the count the same thing? Well, they're not, which means I'm not out of space yet, which we can kind of see here, right? We have this extra space to put things into, so it's totally fine. So what will happen is data will go, and you'll notice that this is index 0, 1, 2, 3. I had to increment the size first, but I guess you don't have to. So we make size equal to 4 because we're adding something, and then we add in a element at index size minus 1, which is the current free element. So I go here and I can add the 1, and there was no problem with that. So that was good. But if I do the next one, you'll notice that if I go to add 8, it will check the count and the size. Now they're the same because I've already filled the array up. So it will go and it will say, I need to make a new allocation. So it will do all that stuff we did earlier with the temp and the data, and essentially we'll end up with a new array. Oops. So this one is after 8, and this one's before 8. And it will say, I'm out of space, I can't add something. So before it adds, it will now allocate 8 spaces, copy everything over. 1, 2, 3, and it will allocate 4 more spaces to put things into. And so now count will become 8. So we said it goes up by the expansion size, and the size is still 4, and as we add the 8, it will go up by 1, just like the last one did, and it will add it to the thing. 3, 4, 5, 6, 7. And the thing to notice is that size, whenever we start this list, or sorry, start this add, will always be pointing to wherever it is that we need to add the element into to begin with. So last run that began at 4, and that's actually where we added 8. We added it at position 4. So if I was to add another number, it's now going to add it at 5, which is pointing. It's not really a pointer, but it's kind of pointing to where we're going to add the next thing. And then we just use the count to basically figure out when do we need to allocate space. So size is not super important as far as the allocation, but just as far as the adding part, and then count takes care of that. Are there any questions on this whole approach? This is a common, simple way to do memory allocation that's a little bit more efficient than just allocating every single time, but it's the same general idea, it's just with one extra step. Okay, so let's do one more thing really quick. 20 minutes. I should be able to talk about this and then the one other thing I wanted to talk about. Oh, can you do an if statement that checks if we've run out of memory and only reallocate copy in that case? Yeah, and actually that's exactly what this part does. It checks if all of the space is taken, if we've run out of memory and reallocate. Yeah. And copy in that case. Yeah, which is exactly that one. Without count. As far as I know, no. You would need to keep track of how much space you've actually allocated in order to know when you've run out of allocation. I suppose you could... that's maybe not the best answer. There is a way you could do it, I suppose. But I don't really recommend it. And we don't know how to do it yet, given... what we've learned. There's ways to catch exceptions, so division by 0 or going out of bounds or something like that. So you could say, what if I try to add and I go out of bounds, then maybe I should allocate more space, and you could do it that way, I guess, and do it without count. But that's a little unsafe in my opinion, just because you're intentionally accessing data that's invalid in order to try to make it work. Although it would work, and I think the exception handler would be fine for it, but I wouldn't recommend doing it that way. But yeah, consider our first example. We added 1 every single time. Uh, Now that I think about it, it wouldn't be much different. Yeah, let's skip the way the vector does it for now. I'm having a little bit of trouble figuring out how it would be different. The idea I was going with was that they would have some pointers that point to the pointers, and then you use that to allocate it. Yeah, actually, let me do a quick thing here. So what they might do is allocate two things. So one would be a pointer list, let's just say. And then they would allocate, actually they would do kind of a combination of these two things. So what they might do is they might have some address like this, or some memory space like this, and this is, let's just say 0, 1, 2, 3, 4, 5, 6, 7 in memory, and then we have something over here, which is way later in memory. This is maybe, I'm using decimal, but that's not realistic. Let's just consider that. This is in hex, usually. 103, 104. Right, so we do some sort of allocation like that. So what they might do is they might increment in blocks like I was doing, where they allocate just more than one space at a time, but then not copy things over. So when I go to do a list.add of 5, what it will likely do is it will allocate some space. Let's just say it does what our program did last time. It allocates 4 blocks and then puts the 5 up there. And then rather than keeping a single pointer, so it will keep a pointer to this. We'll keep a pointer, but what it will do is it will keep track of the pointer to it in a list here. So it will say, I have the pointer 0. So we'll allocate the space and then do the 0. And as it adds things up, so if I was to add 4 and then 2 and then 6, like we did previously, it gets to the case where it needs to allocate more space like we did. And so the thing that was making our program slower, or our method slower, was the fact that we had to copy over every time, which is why we tried to avoid copying as much as possible. So what the vector will attempt to do is it will say, I don't want to copy at all. I'm just going to allocate the new space, keep the old one, and keep track of it somehow. So let's say I do the 3 adds to fill it up, and then I do list.add 7. What it should do is it should go and say the same thing that we said earlier, which is, I've run out of space. My size and my count are the same. I have no more space to put these things into. I need to allocate more space. So rather than allocate something that is still contiguous, it's still, like 4 plus 4 in this case, it's going to allocate 4 more blocks somewhere and then put it all together. What it will say is, I'm just going to allocate the 4 blocks anywhere and deal with it. So it might go and allocate a new pointer and have it point to these 4 blocks. Again, consider that when we allocate something, it's basically random. It's just going to end up somewhere. So I'm going to have another pointer. Just call this pointer 1 and pointer 2. And this will allocate a new space, and we'll just put 7. And what it will do is it will keep track of where this new pointer is. So consider, I didn't have to copy anything over. And if I go to access things, if I know that it's between 0 and 3, all of the data that's located at index 0 to 3 is associated with the first pointer. The thing that is associated with indices 4 through 7 will be at that pointer. So consider that in the actual list, this is element. Let me do this all in blue just so it's clear. 3, 4 through 7. This one would be element 0, 1, 2, 3. 4, 5, 6, 7, because I can't count apparently earlier. And they're no longer right next to each other in memory. And we do have to consume a little bit more space by keeping track of these pointers. But that's okay, because it comes with the really good advantage of not having to copy everything over every time we do an allocation. So note that this one, that's pointer 1, and this one here, that's pointer 2. So it will basically keep a list of all the pointers that point to the data that we've already allocated without reallocating any new data. And so it will just allocate it in blocks of things and then keep track of where it allocated those and use that instead. Way more efficient, way more likely that that's the case, that that's how it works. But it's a little complicated. I don't know if we're really going to test on something like that, but I would still say it's a good idea to know anyways, because this is a practical application, and they may talk about in other classes, and it's just good to know. So any questions on how that works? So that's the actual practical best way that I would recommend implementing something like this. But it is it's maybe a little bit harder to wrap your head around, so opting for something like this is still, that's okay. All right. I'll see if anybody has questions. I'm going to leave this on the screen for just a moment. Okay, let's go back to the program really quick. Let's just talk about one more thing before we have to go. So let's make a new list type that basically does the same thing as this, but it does it with a custom class. So class, we'll just say person list. And I'll copy everything over in a moment. But let's just really quick, let's make a class called person like we did last time that says int name string int age string name. And I'm going to do these as pointers. That might seem a little strange, but you'll see why I'm doing it hopefully in a moment. And I will create some public functions. It's basically the same like example class I wrote last time, just because I think it's simple enough. So we'll do one that gets the name. In that case, we will return the name dereferenced. Considering I have a pointer, I'm going to need to dereference it. It would also help if I did the correct data type. Get age. So we'll keep these as pointers, but the user won't really know. It'll just return the string and the name normally. Or sorry, the age and the name. Okay, so I will create a int. Let's just do this as a capital, just for simplicity's sake. Name, and then we'll make a constructor that just sets those. So age, then again, we need to dereference it with the star is equal to age, and name is equal to name. All right, pretty standard stuff. Just create a person with an age and a name, and then we can get the stuff if we want it later. All right, so let's just do the exact same thing. Let's copy and paste all of this stuff, and then we'll just change it to deal with a person class instead of a integer. Right, so just need to rename the constructor. This stuff should all be the same. This will need to be a person pointer now, which means that version, so I need to return a person now. And then temp needs to point to people or person classes. And then we also need to add people. Add person. Okay. Oh, and then allocate a person as well. To person. The default constructor exists for person. Oh, that's true. Yeah, okay, let's just make that really quick. I think I had this last time anyways. So we'll just say age equals 0, name equals unknown. And I need to dereference these. Okay, now we have a default constructor. It will just allocate those persons. So no suitable constructor exists to convert from int to person. Oh, yep. So I can't return 0 as a default case if we go out of bounds anymore, so I'll just return a new person. I'll do it like that. Okay, that should take care of that. What does this do? Buffer overrun while writing to temps the unsigned 8 but 16 bytes might be written. Unsigned 6. Temp. The writable size is unsigned integer 8 bytes, but 16 bytes might be written because of this stuff. We won't worry about that, I suppose. It's a little strange. The buffer's not big enough for that, but I will. Okay, well, let's do our person list really quick. So we'll say person will is 20. We'll say person Jeff. Did I do it the other way around for my constructor? I had done age and then name. Yeah, there we go. And we'll do Jeff, who's 30. And then we'll just say like Mary or something like that is 40. Okay, so we have 3 people. And then we'll create a person list. And we'll just call that people. And we'll say people.add. We'll add Will. We'll add Jeff. And we'll add Mary. I should do a few more. Let's do at least 5. Yeah, let's just stick with 5. That's fine. So I don't know, Susie and Dawn. For the sake of time, let's just make these the same age. That's okay. Okay, so we have 5 people now, and we're going to add them all to this list. So the reason I picked 5 was because we know after we hit 4 and we go to add the 5th one, it's going to reallocate space, and then it's going to delete all of the old ones. Why is this an error? I think that's just the compiler being wonky. Yeah, so the idea here is that on this 5th allocation to Dawn, it's going to need to do some stuff. So hopefully it gets there. It seems like it does. Maybe. Nope. Age was a null pointer. Oh, you know what? Yeah. Age isn't pointing at anything. So this is maybe a better idea to just say point to that. Perhaps, maybe I don't want to do this with pointers. In that case, I might have to work around it and just come back to it later. Okay, now I got to it. We're just going to assume that's fine. So you'll see here the list should be pointing to, so it has a size of 4, and it's going to add this 5th person to it. And then it has the data, which again, oh wait, no, sorry, that's the integer list. We have people. But yeah, this one also has a size of 4. It's about to add the 5th one. And then it's pointing to the first person, at least it should be. It seems to be pointing to just random garbage. Oh, what's up with that? let's maybe it's the way I implemented it, but let's at least consider what it's doing here. So it goes and it says I need to allocate a new space. So it allocates it as we talked about. It makes more space and then it copies everything over. So it's going to copy 4. And then it goes and it deletes it and does a temp stuff. Okay. So that should be fine. This is just a dumb error. Okay, so now there's something off about what I did. And it has to do with the fact that we're using a class now versus an integer. So very quickly, let's just try to get this example done super fast. I'm just going to briefly draw it. So consider that here I have Mary, and she has a name pointer which points to a string that says her name, and then there's an integer pointer that points to some memory that has her age. And then I have all the other people. So when I go to add that 5th person, we know that the way we had this strategy, it deallocates space whenever it makes the new copy. So it deallocates all the old stuff. Well, consider that that will just delete all of the data there, which is that. What's the problem with me deleting all of that data? And I apologize if this is a hastily drawn image. Maybe it's a little bit hard to follow. I'll probably talk about it more in detail next time. I just thought I'd have a little bit more time. So I'll leave you with that. The problem here might be the fact that by deleting the data, we've deleted this name pointer, we've deleted this integer pointer that belonged to Mary, as well as all the other people that were in there. We deleted all their name pointers and their integer pointers, but we didn't delete the space that was at their name pointer address and their integer pointer address, which means that we didn't actually deallocate all of the space that they had, just the fields that they had. And that means that this is still out there somewhere with nothing pointing to it. This is still out there somewhere with nothing pointing to it. And the same goes with all the names and all of the ages of all of the people that were in that list that we made, which means we have a memory leak. And so that's an issue. And then so the last thing I'll mention, because you might need it for assignment 3, not really, I guess, but it is at least in the code, is that if you put a tilde and then the name of the class person, then that is the opposite of a constructor. That's called a destructor. And what that does is it is called every time something is deallocated or deleted. So in this specific example, and I'll do it more next time, is I would want to deallocate the name. So I would want to delete name and delete age, which is why I did them as pointers, is so I could actually do the deletion part. But in the interest of time, I'll stop there. But the idea, I guess, just last thing to mention, because it does show up in the actual assignment 3, if you haven't started already, is if you want to make a destructor that's called, whenever something is deleted, you give the constructor name, and then you give a tilde in front of it for a destructor. And that's called whenever you deallocate something. Now that also happens whenever something is deleted in the scope of a local. So at the end of main, the destructor is also going to be called in the assignment 3. So just something to note. I wish I had more time to explain it, but if you have questions on it, just let me know on Discord or email. That was just something I hadn't gotten to yet that I realized was in there. Okay, so I guess that's about everything for the day. If you have any questions, I'm going to stick around for a little bit, so just let me know. If not, have a good day. I'll see you guys on Monday. When's your first exam? I don't know the exact date, but it's probably about a third of the way through the semester. So I would say about week 5 or 6. We're on week, what, 4 right now? Oh, wow, that's actually pretty soon. So probably within the next 2 weeks, maybe. I haven't got an announcement about it yet, so I'm not really exactly sure when we're doing it. But probably soon.